Good morning, everyone. Let me know whether you
Good
can
morning,
hear me.
everyone. Let me know whether you
Good
can
morning,
hear.
everyone.
Let me know whether you can hear, everyone. Let me know whether you can hear.
What about now? Yeah, I know, like I'm using two devices, so there's some echo. I hope now it's okay. Can someone confirm? Okay, thank you. So let's start. The last time we just had one class and we were talking about general data structures and how it connects to the module you had last semester. So we're going to move from there. Just to remind you, this is what we discussed, what happened last semester, and the different type of data structures you learn and the related algorithm you learned in last semester. Arrays, linked list, and what they are and how they are different from what we are going to learn now. These are things that we discussed. And the reason for having another data structure module, the different type of modules. We discussed examples. We also got an introduction to what the course aim is and objectives are. Type of things we are going to learn, particularly at a very high level. They are going to be trees, graphs, and hash tables, and how we the type of objectives we have, why we have to learn these things, and the plan for the weeks. We just had one lecture session, almost 2 hours. So today and tomorrow we'll have two more sessions, things that we missed earlier, and the labs, as it was already informed, will start from coming week. We had to cut short a few things because of all this disturbance, but we'll make sure you learn all what is expected. We also spoke about how we are going to have some practical test during the lab sessions so that you get an experience on doing online programming type test. So we discussed this as well, how we are going to get marks. We will have an end exam with the practical, which is 50%, and the other 50% come from labs, and the corresponding practical test in the lab. So these are also things we discussed, and we stopped there. So from that, let's start from this and see how we can proceed. It was mentioned, the first topic we are going to talk about is the trees type of data structure. So today's focus is on trees. In fact, a tree is a very versatile data structure, and it can be used for or is used in a lot of different applications. So we'll look at some of the applications and the type of trees that we can build so that we can use them in the application. That's the overall idea, right? So if you take example, there are enough and more examples where trees type data structures are used. Let me just go to the part. Yeah. Uh, so the tree data structure, as you might imagine, is like the trees that you see, right? So, like when in a tree, you have nodes and then connections between the nodes. But the connections are, we call one-sided. Like for example, there's a message. Okay. So you don't have cycles in a tree, we say. So when a tree with nodes have cycles, meaning you can start from one node, go through a series of nodes to come back to the same node, then there's a cycle. Such cycle, if they exist, then they are not trees. So they are called something else. Actually, they are called graphs. So trees are not, there's no cycles. Otherwise, nodes from one node you can travel to another, but you can't come back to the same node in that traversal, right? So that's the idea. We'll look at a lot of examples and how it works and how to build them and so on. So a few points to highlight. We have exactly one root node, right? So, how we are going to represent or draw or visualize trees is a bit different from how the real trees are in nature. So we'll be representing them by having the root node at the top and then other nodes and the connections or the branches like below, right? So if you take what I had drawn here, it is a very simple tree representation where this is a node and these are three more nodes, and all of these are in some way connected, right? So for example, this node, the first node is connected to the other three through these links, and uh, in a structure like this, the very first top node is having a special name. We call it the root. Similar to in a tree, we have root at the bottom, and then you have branches up, right? So that's the basic idea. So like I said, there's no cycles. That's the most important item, because so if I have like a tree, which is, let's say these two are connected, then we have a cycle, right? So we can start from here, go here, from here to here, from here to here. Then it is not a tree, we have cycle. And also because there's no cycle, if you want to go from one node to another, there's only one path. There's no multiple paths. Uh, right, so these are the terms you will be using all the time when you are discussing about trees. So I'll not spend a lot of time explaining them one by one right now, but these are all the terms that's out there, and as we go, we will learn what they are. So for example, first thing we already know now is the root, right? So root, if you take a tree, there will be just one root, right? So a root, how do we identify, is by looking at the tree, and that's going to be the topmost node. And meaning top node, meaning it doesn't have any parent. The idea of parent and children or child is coming from the, let's say, let me take the same tree example, which is a simple one. So this, if you take this node, it doesn't have any parent, meaning it doesn't have anything above. But if you take a node like here, it has a node on above it, right? So this is one that's above, right? So this child has this as the parent. Same way for the other two children. They also have the same parent. So in fact, this is a tree with just one parent or the root and three children. And then if you take this particular child, the child doesn't have any more children, right? So there's nothing here. But it's possible for us to make a tree like that. Let's take a tree like this. Let's say three parts, three children. Here is one, here is two more, right? So this is also a tree. And in this case, the one I mentioned as children, they are still children to this parent. But then these uh, children node, they also have more children for them, right? So for example, if you take this node, it has three more children. So if you take this node, there's one. If you take this, there are two. And this level, there are no more children. Children nodes, there's no more children. So I hope you understand the parent, children, or child idea. But also there are, now we can think of other ideas. For example, when you have a tree like this with nodes without children, then those nodes are also called the leaf nodes. Leaf meaning there's no more children, they don't have children. Right, so let me just take a step back, and there is some items. So a tree like this is also possible. In a tree like this, as you can see, this doesn't have children. Same for this, same for this, same for this, same for this. And therefore, the leaf node of this tree are going to be this, 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 and this. You can see they are at different places, not at the same height, or not at the same level, we call it another term, right? So the term level, uh, so level is, that's a level, that's another level, that's another level. Right? So by the way, all these are the same level, okay, although they are not properly drawn. So level is another term that we use. We also use terms. So level, you can see all nodes at the same depth of the same level. Then it also brings you to another definition, which is depth. Depth is, as it goes in the definition, distance from the root node. So we also then had to talk about distance. Distance is basically the links, how many links you had to come down from the root to a node is the distance. And the distance from the root down, different levels, are also called the depths, right? So for example, node this, its depth is 1, this, it's 2, and so on. With the depth, there's also another definition, which is height. So height is the total, like when you have a tree like this, height can't be the smallest depth, it must be the longest, right? So that's the height. And one term I missed to explain here is siblings, which is sort of obvious, right? A parent might have multiple children, so they are also called siblings. So these and these are not siblings, obviously. They are the same level, but they are coming from two different parents. Right? Those are simple terms. And you should know all those terms because we'll be using them as we go. So where trees are used, we discussed in the last class about the use of different type of data structures in applications. So here specific application related to trees. These applications are all real world applications and they are only about where trees type of data structures are used. Right. So in fact, like we already discussed in the last class about a file system, right? You know, a file system is an idea of how we can organize storage, right? So when you have storage, how do you organize it? In fact, we have come up with a organizational structure called the file hierarchy, which is a structure where we can keep files uh, starting from a root or a starting point, and from there everything else is divided into smaller parts, right? Folders or yeah, so some sort of containers where we can keep things inside, right? So you can imagine something like you have a file cabinet, which is like everything, like a storage in the hard drive. And from there, how you can bring shelves, inside shelves, maybe smaller shelves, inside that finally you end up having the real file. So that the content of the files, right? So the same idea. So therefore it's a file system are designed using trees. Like if you take uh, an operating system like Windows, Microsoft Windows, they use a type of file system where they start from what is known as the drive itself, like the storage device itself. From the device, we can logically separate the device into smaller parts, and they call them drives, right? Say for example, you have like a C drive, you have a D drive, and so on. You can name them. There is a logic behind why they are started naming from C, D, and so on. If you don't know, you should go and look at the history and why it is happening like this. Why we start the very first drive in Windows as C, very first storage drive, right? Hard drive. And then these drives are already they are in a particular tree structure because you have the full hard drive, and then it's divided into this. And then if you take C drive, obviously, you know, inside C drive, you can make as many, there is a limit, but as many, let's say, as folders, right? Folders with names. And then inside that, you can again make more folders as you prefer. And inside the folders, you might also, so somewhere here, you might also just can have a file, right? And this can have more folders and files here. More files. It can go extend, right? I'm not drawing everything, but it can keep extending. You hope you noticed here, inside a file, we can't have more files or folders, and therefore these files become the leaf nodes in a structure like this. Inside this, we can't have anything more. There are children who can't have more children, right? So in an application like file system, there's a nice mapping between the different type of children, starting from root, right? So root is the storage device itself. Inside that, we can have these drives. They are again children, but then they will be not the leaf one. They'll be leaf if you don't have any files. If you have just only the drive and you don't put any files in it, then they'll be the leaf. But when you start really using the storage system or the file system where you have files, then there will be more children, right? For example, you can just directly have a file here. I'll draw like that. When you have a file there, that will be a child and also a leaf node because you can't have anything more. You can see how a real world application map into the structure we discussed earlier. Okay. So there are more examples. There are things like files. Sorry, the tree structure can be used in other places. Places like markup languages, like or data representation, file-based data representation like JSON or XML, or even markup languages like HTML, different type of versions of HTML. Even programming languages, right? So the programs that you write, they can be represented using trees. In fact, they are represented using trees. Here is an example. The compiler syntax trees, you can see as it says, your code gets passed into an abstract syntax tree before compilation. So a program that you write, like a C program you write, or a Python program you write, or a Java program you write, first the program is translated into a tree before it compiles and finally becomes a machine or some sort of virtual machine type code, depends on whether it is Java, C, and so on. So the high level program is first converted into a tree and then get translated further before getting executed. Right? So generally the execution, as you know, if you have a typical computer, the execution is sequential. You can have things like loops, but which is again, you learn some assembly, so therefore you understand the idea, right? So loops and all work. It's all step by step. Even if it's a loop, you go from one instruction to another, but an instruction that was already executed, and therefore it's a loop, right? But it's all sequential. A tree is not really sequential, but that's an intermediate representation of a program, starting from what you write to what get executed. So we already discussed things like if you want to have some organizational structure represented in a computer, we need, again, trees to represent them. And one other example is the internet itself. How internet works and how data from different places are traveling or traversing through the internet. We follow what is known as routing tables. So the idea is, let's say, for example, if I'm going to, right now, for example, I'm using Zoom. I'm in my computer, and the Zoom servers, in our case, I think they are in Singapore someplace. I think they're in Singapore. I hope you know how to find out. Right. So from there, so the data from here goes there and they come back to you all, wherever you all are. So they all, the data transfer between all this happens through what is known as routing tables. And these routing tables, they are, for example, for you to receive data from what I send or when I talk, whatever I capture coming to you, or the screen sharing, for it to happen, there is not just a single path for it to happen. So for example, if I want to go to Singapore, I can directly go Sri Lanka to Singapore. There are connections, so I can directly go there. Or maybe there is, if that connection is too busy, I can also go to a connection to India from there to Singapore, if it is less busy. So there are a lot of such variables where multiple paths are possible, and therefore such routing meaning from where to go to where, information is stored in a tree type data structure. Right? So, and one other good example is the traditional databases. So databases where we keep a lot of records. Again, uses a special type of trees called B trees, and that is how we are able to use databases to access data really fast. And when I say access, it's not just reading; it's all type of things, right? Reading, writing, updating, all type of things can be done fast. So tree structure is pretty versatile and used in a lot of applications. This is just a small set. By the way, if you have questions on any of this, feel free to ask. So I think I'll skip this now because that is next what I'm going to show in more detail. Yeah, I'll skip these slides and just go to, okay, maybe I can, yeah, I'll go to the next slide. Okay. So I intentionally, when I was drawing trees, I was drawing multiple, like for example, a tree with 3 children. I mean, a node, a tree where the root with 3 children, right? The number of children you can have to a node in a tree, there is no limit. You can imagine, right? So the application I told you, things like the file organization, like file hierarchy or file system, where I can't limit the number of children I can have for a parent, because like inside a folder I can make as many files as I want. Like I told you, there is a limit which is very large, right? So it depends on the number of other factors regarding file system. We'll not go there for now. So, but the numbers can be large, right? So the numbers can be more children, and then they can also have more children, and each one can have more children, and so on. So that's the typical tree. But when I want to make a tree like this large, and if I want to use it for specific application, like the whole idea of building data structures, we discussed this earlier as well in the first class, and I believe we would have discussed it enough times during data structures and algorithm course, module 1. Right. So the intention of having data structures is to improve the access to data. Right. So improve the performance, particularly, not only performance. Performance is how fast we can access data. How When I say access, understand that I'm just using a very loose term, access, but in reality it is reading, writing, updating, creating, all different type of activities with data, right? So how fast I can do is what I mean by performance. How fast I can do these different tasks. The better the data structure is, the faster it becomes in terms of these different type of accesses. And the access requirement are also very different, depends on application. We will figure this out as we go. Just trust me for now. And then the challenge, when you have a data structure like a tree, when you want to build a tree, which is of these multiple nodes, and each node or each parent can have as many children as we want, it becomes a bit complicated. How do I organize, right? So before we go there, let us break this problem into something very simple. The simplest possible uh, tree structure we can think of is what is known as the binary tree structure. So binary, as the term says, 2. Right? Binary is 2. So binary trees is what you see first. We also have something called binary search tree. I'll come to that a little later. So we'll first talk about binary trees. So the idea of binary trees is very simple. the maximum number of children a parent node can have, or any node can have, is 2. That is what a binary tree means. So I'm saying the maximum is 2, which also means there is a minimum. Can you see what the minimum is? Chat. What's the minimum number? Okay. Getting answers. Yes. So the minimum, as you have identified, is 0. Even if you take this particular tree that I have already drawn, right? So even in this tree, yeah, this tree has 3 nodes and 3 nodes, right? And this node has 2 children. This node has 0 children, and this node again has 0 children. These 2 nodes, the leaf nodes, they don't have children, right? So, but this is a binary tree. Why binary tree? Because the maximum number of children a node has in this tree is 2, right? So that's what the idea of a binary tree. So we'll discuss first about binary trees and how we can make a binary tree efficient. Can a binary tree efficient by on its own? Answers to questions like this is what we are going to discuss now. So in fact, like we also focus on the operations and their complexities. A simple complexity analysis, meaning how good these structures can perform, also is part of the discussion. So before we go and start discussing this in detail, you just also have to take a step back and understand where we are heading, right? So we already mentioned that we are going towards a more complex data structure like tree from something like an array or a linked list, because we want to keep the performance. Remember, I introduced what performance means here, but I am sure that you already had discussed it in the last module as well. Keep the performance better, or access to data faster, right? So I'm just looking at some previous data structures that you know, things like arrays. So if it is an array, if the array is not sorted, you know how long it takes to do a search, right? So these are things you have already discussed, right? If you have an array of length n, if you want to find an element which is an unsorted array, an array which is not sorted, and if you want to find an element inside that, how do you find it? Is by going and looking for each element. Right? There's no other way, because the array is not sorted, it's just randomly there. All the elements, let's say you have 1,000 elements, you just have to go through each one of the 1,000 element to see which one is whether the element we are looking for is there, right? So it's as difficult as time consuming as it is if we have an unsorted array. But if we have a sorted array, the problem becomes easier. And I'm sure you remember this discussion and learning. Things like if we have a sorted array, what then we can do is we can do a searching algorithm known as the binary search, right? So the idea of binary search, or the idea of a search which divides the problem into 2 halves. Every time it goes down, we also call this idea of the algorithms the divide and conquer algorithm. The idea of that is you have a tree, sorry, not tree, you have like a list or an array which is long, but then they are all sorted. They are in an order, right? So when they are in an order, then what you can do, if I want to find an element here, I just can go and look at the middle of that list. And if the element I'm looking for is there, then I'm already done. If not, I can check whether the element I'm looking for is smaller than this, the element here, or larger. If it is smaller, then I can just ignore all of this. I don't have to worry about this. I can just start doing it here. So I'm reducing the search space by half every time I look for the next element, the location of the element. So I can quickly come down in time in terms of time, how fast I can do. And the time it takes to do such thing is log n with base 2, right? So the number is much less compare, or the complexity, how much time it takes to do such operation is much less compared to a larger, compare a random unsorted array. When the array is sorted, things become easier. But then we still have problems in certain operations like insertion. I said access, right, which involves multiple operations. If you want to search, it's fast. But if I want to insert in an ordered list, then it consumes more time because I have to put the element I want to put in the right place. I'll have to find the place. Finding the place is faster. But if I want to insert, then if let's say I'm inserting here, then I can't just insert it here. I'll have to move all of these other elements to the other side and insert. In a situation like this, we can do things like linked list you learn, right? So where you don't have to like shift everything down, where you can like bring a node and link them together, right? So there are different ideas. So these are things we are discussed, and we are taking it further with uh, uh, a structure like a binary structure where the searching and also insertion become faster, much faster. Both become much faster. One other interesting idea of something like a tree is that the now we are making a data structure that is like earlier we did with an algorithm. What I mean is earlier we had a linear data structure and we used an algorithm called the binary search algorithm to divide the search space into half, again into half, again into half, and so on. So we did it on a linear data structure. Now the binary tree is the other way around. We don't really have to worry about building an algorithm that takes a linear data structure and divides the space into half, but the data structure itself divides the data into half, and keep them in different places. So it becomes easy. That's the idea. So the data structure, we are building a data structure, so the algorithms become easier. We don't have to build an algorithm that does the breaking into half, dividing and conquering. Normally it's done by the algorithm in a linear data structure. Now we are building a data structure that can keep the data in that way, so we don't have to really build a complex set of divide and conquer type algorithm. We can build just a traversal, just going through the data algorithm, and the rest is automatically taken care of. You will understand more when I show examples, if you already don't. Right. So like I told you, we are talking about binary trees first. Here is an example. I think I have already shown a few examples. So here is one example of a binary tree. So where you have, I think I don't have to explain this, right? So there is left side and right side. So it becomes easier that each node has only just two sides. So each node has only two children, and therefore it's not, it's very predictable that way, right? So if we have a node where if it's not binary, we don't know how many children there would be. There can be 2, there can be 10, there can be 100, there can be 1,000, and so on. So here it's just 2 maximum, and like we already said, minimum 0, and obviously there can also be 1, right? Say In this example, so this one has 2, this one has 2, this one has 2, this one has 0, 2, 0, 0, 0, 0. Right, so there's no node with 1. But if I have a node like that, then, sorry, I deleted some things. I have an outline. No, sorry, I don't know what I did. Yeah. So if now I had to update this, so that node now has 1 child, right? So, and then this node has 0. So that's the basic idea of a binary tree structure. And why it is useful, what you can do about it, let's see as we go. Here is a formal definition. I have already shared, by the way, the slide deck for you to have a look and refer. I already have explained it, right? So what a binary tree is, and the key characteristics is the nodes can have 0, 1, or 2 children. And something else is, if you look at this tree that I have here, there's no specific order anything you see. Maybe there is some sort of an order you see, like 1, it's just randomly we wrote, but then it's 1, 2, 3, 4, 5, 6, 7, 8, 9. But the same tree can also be just random nodes. Like for example, this tree with this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and I randomly putting. That's a very valid, the one I just now drew is a very valid binary tree. So where I have nodes with 0 to 2 children, and there are values which are like the content which are like randomly assigned. That's a valid binary tree. So this one is not very random because numbers are assigned in some order. I think it's done just for the sake of like numbering them, but it's not specifically random. So here it is. So both are okay. Both are binary trees. There's nothing wrong with the binary trees here. Right. So there's no ordering. That's what my point is. In fact, we will also today look at a specific type of binary tree called the a searchable binary tree, where there is an order. Right. So right now there's no order. If there's no order, the problem comes back to what we started originally, which is we'll have to go through the whole tree, all the data, to find what we are looking for. Right. So order matters. Even in the arrays, we realize order matters. Right. So order is, we need some order so that we can search and access data fast. Right. So order is important. And the next easiest thing is, because it's binary, the choosing between element or choosing between children becomes easier. There are only 2. Right? So each child, when you want to traverse, I use this term traverse to mean going through those nodes and looking at what's in there. Right? So traverse will become easier while I have to choose between left or the right. Right? So that is why binary makes sense. Right? And there are different terminology used for the type of binary tree we have, right? So, in fact, something like this term would surprise you, but it's also a binary tree. The binary tree, by definition, can have 0 to 2 children, and therefore we can build a binary tree like this. This children is not there, or this child is not there, and this child is not there. There's a child, and this child is there, this child is not there, this child is not there, this child is there. So that's a leaf node, that's a root, leaf, root, and whatever in between are normal nodes. And this is a binary tree. But can you also think of another data structure which is like this, which is not a tree? Answer in the chat. Yeah, exactly. So that's very much like a linked list. A linked list, the only difference is we by design said there'll be only one node which is connected to this, and therefore it looks very much like that. So and therefore a binary tree what we designed, now what I'm showing you on the right here, is very much like a linked list. The only difference is in a linked list doesn't have a possibility for another link, right? So it doesn't have this. The what I'm drawing now, it doesn't have, right? So that's not there. That's not there. That's not there. That's not there. Otherwise, the potential for having one more node is not there in a one more children is not there in a one more child is not there in a linked list, but in a binary tree, that potential is there. So you can have one more child. That's all it is. Otherwise, the one I'm showing you is very much like a linked list, or we call it a skewed binary tree. All nodes have only one child, degenerating into a linked list structure, right? So it's not really a tree, although it has the potential to be a tree, but it's just a linked list, right? So it has a potential to be a tree because each node can have more than one and more than one children, like at least two children in this example, right? So that's the skewed binary tree. And then there's also other type of binary trees like full binary tree, complete binary tree, perfect binary tree. They are sort of very similar with slight differences. Full binary tree you can imagine what it is. Full binary tree is a binary tree with all nodes to be with two children or no children. Obviously, no children will have to be there to finish a tree, as you have imagined, right? So, like the example we had here. So this one here, we have either 2 or 0. We realize that, and then I drew one to make one child node as well. But in this example, there's only 0 and 2. Right? So that if you have a tree like that, then it is called a full binary tree. So and then there are, like I told you, there are a few other terms like complete binary tree. In a complete binary tree, all levels are filled except the possibility of the last, which is left not filled properly, right? So complete meaning you will have again a binary tree where you have one level with few nodes filled and others not filled, right? But then from left to right. Perfect, all internal nodes have two children. And the perfect one meaning that they are all of the same level, right? So here the level doesn't have to be the same, right? So there are small differences. Sometimes these terms are also mixed up. What we really call a tree. But the whole idea why I'm bringing this topic up is to make you understand, okay, when you're making a binary tree, it's not possible to make a full binary tree all the time because there could be less number of nodes that are out there. You don't have enough nodes to make. I hope you understand when you want to make a full binary tree, you had to have a certain number of nodes. Like you can have, that's a full binary tree. Oh, that is a full binary tree, right? Oh, that is a full binary tree. Oh, that is what. So then only those, right? So which means a number which is of certain sequence of nodes. Not every possibilities are possible. But then there could be a situation where we have odd number of nodes. So then we can not really make a full binary tree or a complete one. But we should not go and make a skewed like a linked list type of. So when you if you're going to go and make a linked list type of binary tree, it's going to be not useful. It's no longer a tree as it is. So those are the difficulties and things we have to be consider when we make binary trees. So to make things more easier and also more structured, right now we talked about binary tree, but we didn't specifically say how to make one, right? So how to search for items there, because if they are not in an order, we also realize searching is going to be not fast as we want, because if things are not in an order, then we'll have to go through all the elements to search. So it's not going to be very useful, right? So to solve these problems, we are going to design some other structure which give that or like a ordered behavior. So before I go into the ordered behavior, I also wanted to just highlight, this is something that I should have done in the last class. Even today morning, I just skipped about how you visit or traverse a tree, right? So let me just quickly explain a little on how you traverse or how you go through a tree, right? Traverse means go through a tree, right? So go through all the element in a tree. So if you have a linear structure, it's simple, right? So you can start from the beginning, go till the end, right? But when you have a tree structure, let's say this is the root, this is the left child, right child. So now going through these elements or going through the values of this tree or the data in this tree, there can be multiple ways to do it. Right, so that is where we talk about this traversal and different ways of doing it. One, what I can do, I can first visit this, number one, and then I can visit here, then I can go here, right? So I start at the highest level. I start at the root, and then I go to the next level. In the next level, I go from left to right, the usual way of rewriting things. So if you are in Middle East and use Arab, maybe you'll use the opposite. Right? So that is one order where we start at the root, then go to left, and then go to right. Right? So like I said, it could also be the opposite. Top, right, left. Right? So depends on whether it's basically we are going level by level. We are starting there, and then this level either here to here or here to here. I'm talking about left to right because left to right is what we normally how we write. It could be right to left as well. That type of an order is called the pre-order traversal. Pre, right? So pre meaning we start with root. Post as opposed to pre is we start with the children first and then the root, right? So pre is starting with root, post is we start with children and then go to root, right? So it's just the opposite, right? So in post order, we will do, so let me clear everything. In post order, what we will do is we'll start this level and then do this level. So I'm taking left to right because we write from left to right, but it could be right to left as well. Right? So in this example, I'm only considering left to right. So pre-order, post order, what you'll do is I'll start here then 3. I'll go in this order. I could have also done 1, 2, 3. Right. So there are two other orders. One is known as the in order. It will make more sense when we go beyond this point of discussion. But for now, in order is you start from one side. Here it's from, let's say, left. So that's number 1. So you go like this. You could also do the counterclockwise, but that's the similar to this. Right? So in this order, it's going to be 1, 2, 3. So counterclockwise, it's to the opposite. So that's in order. Right? Let's take a more complex example, little more complex example, right? So an example like we have a perfect tree history. Now it becomes a little more complicated, right? So in the pre-order, what we will do is we are going to do root first and then left. We have to decide either left to right or right to left. Like I said, we'll be going left to right. So we are deciding left to right. So in pre-order, what we will do is we'll start from the root and then its children left to right, right? So let's say these are numbered or named A, B, C, D, F, G. By the way, the numbering is done just like there's no ordering there, right? So I'm not considering ordering there because ordering is going to be different. These are, let's say, just the labels for those nodes, so it's easy for me to explain. So pre-order will be, I'll do the root, then left, and then right. So when I say left, earlier there was only a node left. Now I also have what is known as a subtree tree of left, right? So if I take this, that's the root. So root first, so A first in the order. And then I have a left subtree. So I'll have to consider left subtree as another tree to do this traversal. So if I have this left subtree, so by the way, I'm started with A, root, and then left first, and then right. That's the order here, right? So root is done. I'm going to the left. When I'm going to the left, it's no longer a node, but a tree, another tree. So I'll consider this tree and do the same traversal for this tree. So if this is the tree, I mean the one I have marked in triangle is the tree, then B is its root, D and E are two children. And that if I do it in pre-order, I already explained a situation like this. I'll do B and D and then E. So when I'm done with the left subtree, I'll go to the next one. Remember, we have done root, left, right. Then I'm going to do the right subtree. So right subtree is this. I'll follow the same process there. So which is C, F, G. That will be the order for pre-order. So if I'm going to do post order, can someone tell me the order or put the order? I'm clearing this. Oops, I cleared. That's the tree. I want you to do post order. Assume left to right. Post order can also be right to left, but we are only assuming left to right in this example. I want the letters. The answer. A, B, C, D, E, F, G, those letters. I'm getting different answers. I want more of you to try. I know like only 5, 10 are trying. Others, wake up, try, and give you like few more minutes. Let's say 2, 3 minutes. Okay, I got more answers, and most of the answers are correct. There are few mistakes, right? So those who are struggling, having issues, we had to follow the same idea I described earlier. As the idea is post order means left right route, or it could also be right left route. We are not taking that option, right? So because we are like left to right people, so we are taking left right option, not the right left option. So if it is left right, so let's take this tree, and we'll start from the root, and we are not going to put the root first because we have to put the left first, right? And the root comes last. So we'll go to left. So I'm going to left. When I go to left, now I'm not at a leaf, I am in a subtree, like I mentioned earlier. Because I'm in a subtree, I can't just take the root and put it as my answer because it's a subtree, it's another tree. Because it's another tree, we'll have to follow the same process for that tree, which means in this tree, what is the left again? I had to find. So I will go here, and that is a leaf. There's no more subtrees. So I'm done. So that's the left I'm going to put. So I'm going to start from D. So I'll finish the subtree first before I go to the main tree. So this subtree, this subtree is something like what I already have explained to you. So it's going to be D, E, and then B, right? So D, E, B, I'll do first. The subtree first, the left subtree first. Then the right subtree, right? So I'm going to do the same thing for the right subtree now. So if I do it for the right subtree, it's going to be this subtree, right? So this subtree again is, I can't do C because it's not a leaf node. I have F. So F, G, C. That's the second set. And then only I'll be doing the root where I started, which is A. Right, so that's the order, that's the post order, right? So most of you have given this answer, some of you have mixed things up. Just pay attention when there is, we are going to display a node, and if the node is not a leaf, then we have to consider it as another tree and do the same thing to that tree. It is the idea of this recursion, right? So you learn about recursion earlier. Here, yeah, it's automatically coming, right? So that's the way how the traversal works. So that's the right order. Those who have made few mistakes, I see some of the answers with mistakes. You will have to figure it out, spend some more time, and try few examples. So now the same I can try in other places, like in order, for instance. Let's take the same little more complex tree. The letters I'm just putting, right? So I'm not using any order. I'm just putting that letters just for labeling things, right? A, B, is. I change the letters, I think, doesn't matter. A, B, C, D, E, F, G. Now, if I'm going to do in order, last time in order was left, root, right, right? So when you had only 3 nodes, left, root, right, every node is covered and I'm done. Now I have more nodes and therefore I'll follow the same idea, right? So left, root, right. So I'm going to start from the root. So left first. So I'm going to come to left. When I come to left, if it is a leaf, I'm done. Here it is not a leaf again. It's a tree, a subtree. So I'll be doing the same thing on this subtree, which means this subtree is an easy subtree, right? Because we have seen such subtree in the previous discussion, just 3 nodes. So this subtree, if I do left, root, right, is what I'm going to do first. Why am I doing that is because I go from B to left. Left is a leaf and I'm done, right? If left has more nodes, again, I'll be applying the recursion. I'll not finish. Yeah, I'm doing C because I have C is a leaf, D is a leaf. That is why I'm finishing here, right? So it's C, left, root, which is B, and D. The left is now done. Then the root, so A, then the right. Right again is not a leaf, it's a root, it's a tree. Therefore, I'll have to go through the same process. F, E, G, right? So C, B, D, A, F, E, G is the in order list for this tree. So you should try more examples. The level order is a very simple one. I didn't even explain it last time, but it's so obvious. But it has very limited applications. So we will not spend a lot of time on it. So level order is just visit level by level, either left to right or right to left, depends on which tradition you are coming from. So in our case, we'll do left to right. So it's very simple. But like I said, it has very limited applications. So level order is visit nodes by level by level from top to bottom, left to right. So level by level, top to bottom. So we are going this way, and left to right because we are from Sri Lanka and we write things left to right. So A, B, so that first, and these two, B, E. So A, B, E, next level C, D, F, G. That's a simple thing. In fact, for us to understand, for us to explain and remember, this is a simple thing. But for an algorithm to do this, level order traversal is not so straightforward. It's a bit more complicated because there's no links between these two, right? So these one, like the links are here, links are here, links are here, links are here. There's no link like the way I'm looking at directly, right? So there is indirectly obviously link. So it will be A, B, E, C, D, F, G. That's the order. And so that's not very useful, but one of those, that's also an order known as the level order. So this is a simple idea on how you traverse through a binary tree, right? Have you got an idea? If not, you'll have to try more and verify, right? So how do I represent a binary tree? You will do a lot more about this in the lab, so I won't spend a lot of time. Depends on the programming language that you use. I hope you have learned, you have already, not I hope, you have already done things like linked list. So now the tree is a little more complicated. In a linked list, it would have been a node like that, right? Now, if you have a doubly linked list, obviously you would have also had one more node, one is to the front, one is to the back. I see that some of you mentioned about singly linked list. So you'd have also learned about doubly linked list. Doubly linked list is a linked list where both sides are connected, right? So you can traverse back, front and back without going to the start, right? You can travel both sides. So it makes it easier, but it's more bulky because you have more links. More links means more memory, more storage, and so on. That is doubly linked list, but doubly linked list would have also had one additional one additional entry in a node structure where you had to have front and back. So here it's not front and back. The binary tree will have left and right. Each node you can have two links, one to the left and one to the right. That's the simple idea. And when you start implementing, you could use your own programming language of your choice. I mentioned in the last class as well, I'll be showing examples which are more pseudo, or I'll use C type of data structure. In fact, like this is C type of programming language. But then it's up to you to decide which programming language to use. We won't be restricting you on the programming language. So, but then binary tree has certain issues like we already have mentioned. I mentioned this earlier as well when you're talking about sorted list. So binary tree by default is not sorted. So it's automatically not sorted. So the order in which the tree appears, the element appears can be any random, which means if you want to find whether an element exists and search for one element or insert elements, insert we can obviously do anywhere we want, but we've had to figure out where to do it, right? So one more obvious choice would be we do it in a place where the tree becomes more balanced or more perfect, right? So that's what always we'll think of making the tree as balanced as possible so that we can use the best out of the tree data structure, right? So, but anyway, binary tree is not sorted. And when it is not sorted, there's a potential that the tree can become very skewed. We saw an example like a linked list. Then the whole purpose of building a tree is gone, right? So therefore, we had to come up with a tree structure that is most organized or more sorted, actually sorted, and a proper data structure, binary data structure, binary tree data structure that is ordered or is known as the binary search tree. You can see the term search in it, which means it's not just a binary tree, it's a binary tree that we can easily search in, right? So that's why that's a binary search tree. So in short, we also write it as BST. So if you see somewhere BST, it means binary search tree in data structures, that is. Right, so we'll look at how binary search tree works. It's all binary tree anyway, but it becomes a bit more organized and sorted. How are we going to make it sorted? Is through certain process we are going to follow, right? So when it becomes a binary search tree and things are sorted, then searching becomes easier. We don't have to go and search everywhere. I'll show you example. We'll be searching on a specific way and make it more easier. So ideally, in a proper binary search tree, the search time will be in the order of log n, right? So it's the same like a binary search. in an ordered array in a binary search, the time that takes is log n, we discussed earlier, right? So here it's an ordered binary search tree, and therefore the search time is or log n. So you might ask me, why would I have to do a tree instead of a linked list or an array which is sorted, right? The good part is there somebody had to sort, right? Or in a linked list or an array, somebody had to sort, and if it is not sorted, the putting a new okay. So let's say if it is a sorted list and already sorted one time and it's sorted, but if I want to insert something new, that insertion, if I want to do it properly, or if I want to maintain properly the sorted list while inserting, it consumes a lot additional time compared to a binary tree. So binary tree, or particularly binary search tree, is better in certain operations. But searching, it will be similar to a ordered array and do a binary search. One other benefit is binary search is a more complex algorithm. Searching itself is not easy in a binary search because the structure is linear. You'll have to write a program to go through it in a certain way, divide and conquer algorithms. So now in a binary search tree, because the tree is already automatically be sorted and it's a tree, and the algorithm becomes so simple. I'll show you how. The searching algorithm in a binary search tree is so simple, not like a divide and conquer algorithm. By the way, this is also divide and conquer, but it becomes so simple because because it's a recursive algorithm. Recursion involves here in a very simple way. Actually, it's so straightforward. So those are things that makes a binary search tree better than a ordered list and binary search algorithm, right? So, but both of them will do the search part of the operation at the same speed. So here's an example of a binary search tree, right? So when you have a binary search tree, we are talking about having an order. So let me show how a list of elements like this can be or will be may put together to make a binary search tree. So we'll start from the first element, 50. So 50 will be the root node. Next element 30. So 30 is an element which is 30 is smaller than 50, right? So because it's smaller, so smaller things will keep on the left side, larger things will keep on the right side. So 30 is going to be just here, left side. 70, the next element. By the way, every time we find an element, we'll start from the top, from the root. So 50, this is 70, that we have is 50. 70 is larger than 50. So we can keep this in the left side, sorry, the right side, larger. So now if you look at this tree, before we go and insert the rest of the elements, if you just look at this tree, the one we already have made, every node you take, the left side will be lower numbers, right side will be larger numbers. But here there are only 3 nodes, so that's not much to say. One more thing about this tree is now in a tree like this, a binary search tree, if you do an in-order traversal, I hope you remember in-order traversal. In order, left, root, right. If you do an in-order traversal, then you get a sorted list. See, left, root, right. So 30, 50, 70. So remember, we didn't put the elements in a sorted order. We just put them randomly. But and then we did an in-order traversal, we get a ordered list. Right? So that's how easy the data structure makes the data into an ordered thing in a so fast fashion. We haven't worried too much about it. What he said, every element, left side is smaller, right side is large. That's what they are doing. Let's continue and put the rest of the elements. Let me just take a step back to get some of this. Right, so let's go on. 20. So 20 is, we start here. 20 is smaller than 50. So we come here, left side. 30. 30, 20 is smaller than 30. So we'll put 20 here, left side of 30. And we are done. Next, 40. 40 will go 50. 40 is less than 50 here. 30. 40 is greater than 30. So we put 40 here. Next, 60. 60 is greater than 50. We go this way. We have 70 here. So 60 is smaller than 70. So we put to the left side of 70. That's 60. 80, I hope now you have seen, I don't have to explain here. Because 80 is greater than 50, so we go this way. Here it is 70, this is 80, so 80 is greater than 70, so we put this way. So now we have made the whole binary search tree. So that's a binary search tree, right? It's a binary search tree. Every node you take, everything on its left side will be smaller than that particular node. Everything on the right side will be larger, right? You can pick anywhere. Let's say this node. Just left side and right side. See? Everything on the left side is smaller, everything on the right side is larger. You can pick anywhere. Everything on this side is large, everything on this side is small. So that's how it has become by we following a particular simple rule. Left side is smaller, right side is larger. And then the list was in some funny order. And here we have an ordered structure. What I mean by an ordered structure is, let's do an in order traversal, right? So let me do an inverse in order traversal. Oops. In order traversal. Remember in order traversal. In order traversal is left, root, right? So we are starting with the root, left, root, right? So we are starting with the root 50. We don't do the root first, we do the left first. So we are going to do this, but this is not, oops. Whatever reason, 80. Right. So we are going to go here, but this again is not a leaf, and therefore that's a subtree. We'll take the subtree. So subtree, first one is the left again, root, right? So it's going to be 20, 30, 40. Then the root, which is 50. And we'll do the same thing for the right subtree. So it's going to be same order, 60, 70, 80. And you can see an in-order traversal give me an ordered list. 1, right? So that's just traversal. It's not only about traversal, even if I want to do a search of an element, right? So let's go back. Oops. If I want to search for an element, let's say I want to search for 60, right? If I want to search for 60, what do? I'll go and check at the root. 60, this is 50, this is 60 I'm looking for. So 60 I know should be on the right side because 60 is larger. I find this, it is 70. 70 I know is larger than 60, so 60 should be on the left side. So I'll start from, let me change the color. I started here and I came here and I had to go to the left side. There is 60. So what did I do to search? I found 1, 2, 3, I found the answer. I didn't go through all 7 nodes. When it becomes larger and larger, this is become even easier because the number of nodes I'll go through to search will be just maximum the height or the levels. Right. So I'll find the answer when I do it. And also in a level, I'll just do one search. Each level I'm going to do one search. So this is a simple one, therefore it's easy. But if you have a little large binary search tree, a node can, like this level can have 4, next one can have 8, 16, 32, 64, and so on, right? So it goes down. But I'll not have to search through all 34 or 16 or 64. I'll 32 or 16 or 30, 64. But I just will be searching, looking at one to go to the next level because they are in the order and these are binary search trees. So searching becomes so easy, right? Insertion and deletion are also easy. Insertion we already saw, right? So we have been inserting elements to this tree and it was very straightforward. You just had to locate the place. Deleting is a little complex, not always, sometimes. I'll explain that. Any questions you have? So I'll go there. So in fact, I have done the insert. Searching, I already explained. I'll not. So searching in terms of an algorithm, or in fact, here it is the C code. It looks like this. I explained it. So I'm something that you can see here is we can do it in recursion, right? So because if I go to left side, it's just a left subtree again doing the same thing, right? Until I find a null or a rule. Okay, so somebody a different question: how to download the slides I have? I think there should be a download option. My slides are in this app called Gamma app. I think there's a download option in the view. If you don't have it, let me know. I will give you a link for a download, a PDF or a slide, whatever it is. Let me know. Okay, any other questions? So binary search tree implementation you will do if we have same number like, okay, if you have duplicates is one other question. So when you have duplicates, there are multiple ideas. One is just to keep the frequency, how many times one number appeared. By the way, a binary search tree, you can't have duplicates. So duplicates are basically the same entry, right? So not separate entries, not separate nodes. So there'll be only these nodes are unique. So duplicate question, that is the answer. So how do we manage it? If you need to keep the duplicates, one way of doing it is we can keep the frequency. You can say, okay, this number appeared 3 times. So we'll have to have additional data structure, additional fields in the data representation to keep the frequency. So there's another question: is the lab classes practical test going to be in Python? Yes, we thought we'll help you with Python because you did the previous module in Python. But like I said in the last class, those who missed, what I said was if you are really want to understand how these data structures work and how they are implemented in detail, a programming language like C is best, but we'll support Python. Yeah, so like Python and C both will support, or even we can consider the programming languages as well. So because what we are trying to learn here is how the data structures work, so programming language doesn't really matter. So in short, the question you asked, we will support Python. So apparently there's no download option for the Gamma app. I will give you a PDF to the same place in the in fields. Anything else? Okay, so let's move on. Insertion I already explained, therefore I will not spend some time now. The idea of insertion is very much like searching, like that we are showing you example, right? So we are searching, and when we find a place, we just put it there, right? But deletion is a little more complex. So I'm going to explain deletion, right? So deletion is complex only in certain cases. So let's take 3 cases in deletion. One, a very simple case. The simple case is if the node we are going to delete is just a leaf, right? So we have a tree, a binary search tree, that is. And if the node I'm going to delete is a leaf, right? This or this or this, it's straightforward to delete. You just can delete this connection, and or we can just delete this from the memory, right? So if you're allocating, we can free it. If it is something like Python, we can just disconnect this link and automatically the garbage collector will remove this, right? So depends on the programming language, it's different, but the idea is it's straightforward. So we find the node, and if both the left and the right pointers, the two sides, this and this, there's nothing here, then we can just delete it, right? So action, simply remove the node by setting the parents. So we can just say this one doesn't have anything, so whatever here will be gone, right? So that is true for any leaf. So leaf node, it's straightforward to delete. There's not much to do. That's case one, the simplest case in deletion. There are other cases which are a bit more difficult, not so straightforward. So let's look at the other cases. So the second case is when you have one child, right? Okay, so there's this request to provide code skeleton in both Python and C. Okay, I'll talk to the instructors and see whether that can be provided. I think they are planning on giving one, but yeah, we'll try that. So that will make your life also easy, and you can also try out. So those who are Python, I think it's going to be very straightforward. C is going to be a little more difficult, but I would strongly suggest you try C option, where you will learn a lot more about data structures and how these things really work. Because the module is not only about just learning data structures, and also learning how these data structures are built. What does it mean to have a data structure, so that you can design new data structures, which are a combination of all these basic data structures. Yeah, so the skeleton code, I'll ask the instructors to provide for. Move on. So when you have one child, it again becomes not so difficult, right? So right. This example, that is, okay, it's a binary search tree now, right? So it's going to be in a nice order. 1, 2, 3, 4, 5. Sorry, that can't be 5. 5, 6. So that's a binary search tree, right? So every element is on the left smaller, right larger, right? So a binary search tree like this. Now, I was talking about deleting 135. 135 you just can delete, right? Nothing will happen. Let's see we delete 3. See, it's still the binary search tree, no issue. Delete 5, same, still the binary search tree, no issue. Delete 1, still the binary search tree, no issue, right? So even if the other elements are there, right? So even if you delete 1 and 3 and 5 are there, still it's a proper binary search tree. If you delete 5 and 3 and 1 are there, still a proper binary search tree. So no issue, you can delete leaf without any issue, right? So the second one is deleting a child. I mean, deleting a node with one child. Example is 6. If I want to delete 6, what do I do, right? Node has exactly one child, could be either left or right. In the case of 6, this node, the child is on the left, right? So if you want to delete that, then the idea is again not so difficult. Replace the node with its only child, right? So what we have to do is we can delete 6, make 5 the 6, right? That's going to be 6. So we put 5 there in that place. So meaning we connect. So this 4 is connected, was connected to 6. We make 4 to connect to 5 and delete 6. That's what we are doing, right? And therefore 5 becomes a level up. So it's not difficult. So if you have, then it will remain a binary search tree. So if we have one child, we just make the child. By the way, the child could have more nodes, no issue. There could be more nodes here, no issue. So by the way, in this example, the more nodes, if it is 5, this node should be something between 4 and 5. This node should be something above 5, right? And or between 5 and 6, if 6 is also there. Now we are talking about deleting 6. So we can make 5 here. If there are more nodes, it will become like 5 the other nodes below. Still it works. Right? So one child, again, no big issue. We just can take that node out and put the child as the node, or the child, the subtree that comes with the child as the subtree, where the deletion happened. So it works. The little more complex one happens when you have two children, right? So when you have two children, it becomes a little more difficult, right? So when you have two children, how do you delete? Is you will have to figure out which one to delete and how to proceed with the successor, the node that we deleted, which one to put there, right? Two children, we cannot simply delete like I had told you here. So to find the replacement, so we had to do the in order successor, smallest value in the right subtree or the largest value on the left subtree, right? So because there are two, right? So now we want to talking about deleting. We are talking about. So if you want to delete this node or even the root, right? So let's say we have to delete this. If you're going to delete this, then which one becomes the root? What is the question, right? So which one becomes the root? Can you tell me which one can become the root? Let me put the numbers. 1, 2, 3, 5. Which one becomes the root? If I delete 4, which one is the root? So I get different answers. I'm getting 2 and 5 as the answers. Any other answer? Okay, that's the third answer, 3. The only answer I didn't get yet is 1. I can make this problem a little more difficult for those who are saying 5. Let's say there is 4.5 here. I made the problem a little more difficult. Are you all going to say the same answers again? In fact, if you carefully think about it, there are two possibilities. The possibilities are not 2 and 3. Oh, sorry, 2 and 5. The possibilities are not 2 and 5. The possibilities are, the easiest possibilities are, from this list, you know what the rule is? We are deleting this node. So the node that's going to come here should be the one between these two trees, right? Between the two trees. What are the numbers that are between the two trees? It could either be 3 or 4.5. That means it could either be the largest number here or the smallest number here, right? It could be one of the two, right? So that's the very first thing. So it can't be anything else. 5 was okay earlier. You all said 5 earlier because there's nothing here. So the smallest number here is going to be 5, obviously, because there's only one number, right? And the largest number here is 3, because that's by the way, there are more numbers, but 3 is the largest. So it could be 3 or 5 in the previous tree. Why 5? Not because 5 is just a child, because 5 is the largest number there. When I also put 4.5, it becomes more complex. So it's no longer the largest number. The smallest number is not 5. The smallest number could be is 4 point, not could be, will be 4.5. The largest number from the other tree is 3. So it should be one of the two, right? So now it's a matter of figuring it out, which one of the two to use. We could use one of the two, right? So either the smallest from the right side or the largest from the left side, right? So to make sure the tree structure is still maintained. So obviously, when you are copying the largest or the smallest from one of the sides, we'll also have to delete that particular node, right? So we'll basically copy the largest or the smallest from one of the sides. We can decide one or the other, not a big deal. But after deciding that, then we'll have to delete that particular node. By the way, the largest or the smallest will always be a leaf. Hope you understand that. Therefore, it becomes an easier problem, right? So the one you're going to delete, let's say we decide in the smallest, I mean the left side, which is the largest. So we'll take 3 and put 3 here, and we'll delete this node. Deleting this node is easy because it's a leaf. And now it again is a proper binary search tree. So it's a little more, not so complex, but little more complex situation here when you have to generate. The root could have been 4.5. Then I would have delete 4.5 node and keep the rest as it is. So deletion is a little more complex as we discussed. And therefore, I am also saying like it could be a question that is normally asked in an exam or somewhere. Right, so talking about complexity is one other thing. I remember from the very beginning, I was also telling you that we also had to worry about how complex this, I mean, how much time these things consume. And also I explained to you, if the tree is properly ordered and properly balanced, particularly, ordered is obviously matter because we are talking about the search tree. But the more important item is balanced. If the tree is not balanced, then we are going to lose the benefit of a tree. A skewed tree is not a good idea. But unfortunately, although I tricked you earlier by giving you a tree with these elements, right? So remember, we made a tree with these elements, and I have specifically put a tree order, although I just pretended it random. The way I inserted these numbers, we have a proper tree built. But if you have an ordered list given, let's say you have given 1, 2, 3, 4, 5 and ask you to make a tree. What will you do? You start with 1. Next one, 2. 2 is larger than 1. Next one, 3. So 1, 2 larger than 2. 4. 1, 2, 3 larger than 3. 5. Here. So you can see if I give you an ordered list and ask you to make a binary search tree, you will make almost a linked list. So making a binary search tree from a random list, there should be some way so that we can make a proper list. I mean, sorry, a proper tree, right? So this tree is not a proper tree. If I have an ordered list, I get a skewed tree. So if I have a random list, I get a okay tree, but I can't guarantee it's a balanced tree. I hope you understand because the list is random. Random doesn't give. So although I pretend that this is random, it is not. Right? So there's a problem in that way. The problem is when I'm making a tree, binary tree, and if the binary tree is like if the number that are coming in are not in a certain order, then I'm going to end up in a worst case skewed tree. If I have the number nicely coming, I can make a proper binary tree, balanced tree, right? But I can't expect the numbers to be in an order, right? So numbers are coming the way they come. I can't expect them to be in a certain way so that I get a balanced tree, right? So that's not possible. So what can we do? If I want to make a binary search tree, a proper balanced binary search tree, but the numbers are coming in a random order, they are going to, what can I do? Can you give some idea? What can I do? I get numbers coming in some random order, but I want a proper balanced binary tree or binary search tree. In fact, the answer is just mentioned here. So we'll have to come up with an idea of a self-balancing tree. We'll have to have a tree that balances itself when we are adding new numbers, right? Like for example, when I have the numbers like 1, 2, 3, 4, 5, if I just make a tree, it's going to be like this. We already saw, right? But I can make the tree a bit self-balancing, meaning when I get 1, this is the tree. When I get 2, this is the tree. When I get 3, I should make the tree like this. So the tree, third one, I don't put it here, but I balance the tree. I do something to make the tree like this. When it is 4, maybe it's here. When it is 5, I don't keep it like this. I'll have to do some more balancing. I'll have to make maybe 3 the root. Just I'm giving one idea, right? 2, 1, 4, 5. Obviously, this is not the perfect balance tree, but it's better than what I originally had. So I'll have to figure out a way to make these trees balanced. In fact, there are ways of doing it. And the next class will in fact look at how this can be done. The problem is this automatically balancing the tree, right? So how do I balance it? What we'll be discussing next. Today we have just seen how a binary tree works, how we can make it a binary search tree so that searching becomes easier. But now the binary search tree, when I'm building one, if I just build it the same way, just follow a simple rule, I could end up in a really bad tree and not use the impact of a tree. So I'll have to come up with a way of automatically balancing the binary search tree. And there are different ways to do it. One such way is called the AVL trees. And there are other ways, like there are red black trees, few other options. We will look at how we can do it using ABL trees, which is a balanced tree, in the next class, which is tomorrow. Thank you very much. And yeah, so I think I hear that you also have a lecture at 12. Very strange, but I'll let you all go. Thank you very much.